We're going to wrap up here this transition metal coordination compound chapter. Last time we got into at the end there, crystal field splitting. And crystal field splitting is this idea that our d orbitals in our transition metal, based on the ligands that are present, for example, with a coordination number of 6 and an octahedral arrangement, we'll do some splitting of those 5 d orbitals. And in the octahedral arrangement, you'll get 3 on the bottom, 2 up on top. And the crystal field splitting is the energy difference here between the lower d orbitals and the higher d orbitals. And depending on the ligand, there are some that are sometimes called a strong field, and there's some that is a weak field. And a strong field will give a separation in terms of energy of these orbitals pretty large. And that does affect how the electrons in that transition metal will populate the d orbitals. For example, if we did have a large or strong field, we would probably see the electrons come in. And at this point, it will decide it's too much energy to go up to those 2 higher energy orbitals, and they will actually fill the bottom first until maybe they have to go up there or not. And what that will do is give you a lot more paired spin in terms of the electrons. And this is what is called a low spin complex. Again, a lot of paired up spins rather than unpaired electrons. The opposite is true as well. You can have maybe a weak field ligand, and this here will be a smaller sort of separation. And the idea here is as it goes and fills, it will decide, and that's not too bad. They will just kind of feel like normal. And the result of that is you'll have a lot more unpaired electrons, which will give it what is referred to as a high spin complex. And again, typically speaking, a lot of times these questions will ask you how many unpaired electrons there are. Is it high spin or low spin type of thing? What determines that, as we talked about last time, is sort of this series here, and sort of it's weak heading in that direction, sort of large or strong heading in that direction. As we talked about, sometimes it does not matter, depending on the number of electrons you have, as it's strong or weak, because you may not even get up there or have enough electrons to sort of get up there. Any questions out there? So we did look at a couple, I think, last time, but just to do one more here, just to again illustrate what's going on. So if we leave this guy here, which is our iron, with our 6 cyanides here. Coordination number here is 6, which will give us our octahedral splitting. This is -1. There are 6 of them, which gives you -6. The oxidation state here of iron is +3. Iron neutral there is 26, which means in a neutral it's got argon 4s2 3d6. In a +3 sort of oxidation state, remember we are going to lose the s's first, and then we will take out the next electron there in the d, and that will give us an iron with a +3, and that will basically have argon 3d5. So it's these 5 electrons again that we're talking about in terms of this sort of splitting that will happen. We can look at the ligand that's present, and again, looking at our list there, we see CN is a strong field ligand. And what that's going to do, again, because this is octahedral, we will get those squared guys up on top, and we'll get the kind of non-squared d orbitals on the bottom. And this is going to be relatively large. And I probably shouldn't draw that arrow right in there. So I get rid of that there. So that splitting is going to be relatively large here. And when it goes to distribute these 5 electrons, it will go 1, 2, 3, and again decide not so great. We don't want to go up that high. 4 and 5 going to give us basically 1 unpaired electron. And obviously this would be a lot more paired up electrons than unpaired electrons, and this would be a low spin complex. Any questions on that there? Okay, so that is octahedral specifically what we're looking at. Now, and again, here you can see here, as opposed to F, it was more of a high spin complex, a lot more unpaired electrons happening. Again, if we look back at X there, or F, it is to the left there are water, which means it's more of a weak field ligand. So the difference between those higher and lower d orbitals are not going to be all that much happening. We got a lot more unpaired electrons happening. Here's all the different arrangements for low spin, high spin, and again, in an octahedral arrangement here on our high spin, that's going to have a smaller crystal field splitting, and that's going to allow those electrons to go in one at a time. Low spin, we're going to start filling up the bottoms before we even attempt to try to go up there with no other option. Now, another sort of crystal field splitting occurs when you say have a coordination number of 4 in a tetrahedral geometry. And remember, 6 electron pairs is kind of like our coordination number of 6 is kind of like 6 electron pairs in geometry. That's octahedral. 4 coordination numbers kind of like 4 electron pairs tetrahedral. But remember, for 4 as well, you could also have square planar, which is again like the expanded octet that could happen. It is the same sort of splitting, except that those guys that were previously lower in energy actually become higher in energy, and those kind of squared guys actually are lower in energy. So if you had something that was in a tetrahedral arrangement, it would work the same way. If you had a large value for crystal field splitting, you would get everybody pairing up first. And obviously, if you had a small value for crystal field splitting, then everybody would go in basically one at a time like normal and pair up. So tetrahedral is pretty much identical there to octahedral, except it's reversed in terms of the orbitals that are on the bottom. Now for geometry as well, like I mentioned, you can have, maybe if we'll turn the slide there. Yeah, square planar, which is also coordination number 4. Get a little bit more difference here in terms of the arrangement, but the idea here is still the same. Here we have our separation and our filling of our orbitals. Again, it's going to go lowest to highest. So for us in this class, we're not going to worry about this square planar because it's a little crazy. You are responsible for octahedral, which is the one we did, and also will be responsible for tetrahedral, which is basically like octahedral, just upside down, basically. Any questions on that there? All right, that wraps up this chapter. Not so much to go. It's actually 21, actually. So radioactivity and radioactive nuclei are nucleuses that will really spontaneously decompose into a smaller nucleus. Essentially, they will a lot of times continue the decay process until they hit something that is stable. When we have something that's going through radioactive decay, sort of the original nucleus there is sometimes referred to as the parent nuclide. And what is made as a result of sort of the decay process, sometimes referred to as the daughter nuclide. All nuclides, pretty much after 84, are radioactive. That brings you to a lot of things on the periodic table on the bottom 2 rows, where we have a lot of those sort of radioactive elements, also a lot of those sort of man-made elements, which are radioactive, because that's sort of how they make it. Now, when we talk about radioactivity, there's several different types of radioactive sort of particles that we come across in nuclear chemistry. You may remember Rutherford, right? He did that gold foil experiment. He shot some alpha particles at pieces of gold foil. Alpha particles are alpha rays. They have basically 2 symbols that are very commonly used. That's a 4-2 helium, because it's basically helium, or sometimes people will actually just use the alpha symbol with a 4 and a 2. By the way, the number up on top is the what number? That is the mass number, yeah. Guy on the bottom is the atomic number, right? And the atomic number is the number of protons, right? And the mass number is the number of protons and neutrons, yeah? So number of protons plus the number of neutrons, and our atomic number, right? Our number of protons. You can find the atomic number right on the periodic table. Every element has its own unique atomic number. You cannot find, as a reminder, the mass number on the periodic table. So a reminder that the number on the bottom is not the mass number, that's the atomic mass. It is different. Beta particles are basically an electron, and that's also the symbol that's oftentimes used. An electron with a 0 and a -1 are a beta symbol. With a 0, -1 are the symbols that are commonly used here. Gamma rays are pure energy. If you remember the electromagnetic spectrum, you'd find gamma rays at the very end of it, way past X-rays, and has a very short wavelength, a very high energy. The gamma symbol is typically used, and zeros on both of those. Now, in addition, we also sometimes have some what are referred to as positron emissions. Positrons are maybe like an electron with a better attitude, but it is a positive electron essentially. And the electron is used there as a +1. And they also will use the beta symbol for this as well, but we'll do a +1. So this can sometimes cause confusion for people as they kind of use the same symbols. Obviously, one's -1, one is +1. I would say 99.9% of the time, if you just see a beta written in a problem, they probably are talking about a beta particle. They usually will distinguish a beta particle from a positron for sure. Even if they kind of did this bare bones type symbol, they oftentimes might even just put a positive up on top to let you know it's like a positron, or obviously they will use the full symbol on all of that. So if you see just a sort of by itself beta symbol, probably going to be the beta particle. And again, usually they'll distinguish that positron. There's also a nuclei that can undergo a reaction that's known as an electron capture. And there is some terminology that we sometimes see in nuclear chemistry that you should understand. When it says something like this thing goes through this type of decay process, that particle will end up on the product side of the arrow. If it says it emits a particle or goes through this type of emission, like an alpha emission or an alpha decay, you would put the alpha particle on the product side of the arrow. Now, if you have something like we see down here where it says, hey, we have an electron capture, then the electron would actually go on the reactant side of the arrow. And sometimes people will say something like they bombarded a nucleus with neutrons or something like that. So if you bombard something, you're basically shooting particles at something. And that basically would also go on the reactant side. So anything that's emitting, anything that's giving off this type of particle through a decay process, those guys end up on the product side of the arrow. Anything that's a capture, anything that you're bombarding something, those particles end up on the reactant side. So as we talked about, the atomic number there is on the bottom and our mass number is up on top. A reminder again that all those things, protons, electrons, and neutrons, they all should be positive whole numbers, including the mass number and the atomic number should always be whole numbers. As you know, again, every single element, as I mentioned a second ago, has its own unique atomic number. So it really is the atomic number, the number of protons. It's important to know what element you're dealing with, as everybody has their own. Some other symbols that you do come across in nuclear reactions is a proton, and a proton is symbolized by one of these two sort of symbols, either a P with a 1 and a 1 or a hydrogen with a 1 and a 1. And also super common is neutrons in these type of reactions. Um, so when we do these type of things and these nuclear reactions are very different than chemical reactions. In chemical reactions, what happens is it's all about bonds and electrons, basically. So all we do is break bonds and make bonds. And that's why in a chemical reaction, right, we balance the equation. If we started with 4 carbons, we end with 4 carbons on the product side. Nuclear reactions are completely different. Nuclear reactions are all about the nucleus, and inside the nucleus is the protons and neutrons, and changing protons to neutrons, neutrons to protons, and so forth. So in nuclear reactions, we do not get sort of the conservation of elements. We actually make new elements on the other side of the arrow. So there's not that sort of consistency that you see in a chemical reaction, because in a chemical reaction, we don't do anything with the nucleus. Nuclear chemistry is all about kind of doing things with the nucleus. Now, when we talk about these particles, they can basically penetrate further into, for example, the tissue or a piece of lead. So as you can see here, alpha particles don't penetrate super far. Beta does get a little further. And if you're ever dealing with something that is a gamma emitter, it goes pretty far. And this is really important, especially if you ever work with something that's radioactive. You should always know what type of emitter it is, because depending on what type of emitter, it may require something just like gloves and a lab coat, or it may require some lead and a lot of distance and stuff like that. So depending on the type of emitter, and obviously gamma is a much stronger emitter than, say, something like alpha or beta. Here's again those symbols, and as I mentioned before, sometimes they will kind of write beta and positrons like so. You can definitely distinguish between them. Now, balancing nuclear equations are extremely hard, and again, because we don't have the conservation of the elements. By the way, I'm lying. It's super easy. You just got to add, basically. So if you know how to add, you should be in good shape. So how we balance a nuclear equation is, again, different than how we balance a chemical equation. Because we do not have the conservation of the elements, what we are doing when we balance an equation is, when we look on the left-hand side of the arrow, all the mass numbers, when you add them up, pretty much need to equal all the mass numbers on the right-hand side of the arrow. So basically all the mass numbers need to equal each other. Now you can see here in this equation, by the way, we do have a coefficient in front of the neutron, and that coefficient does need to be multiplied by the mass number and the atomic number. So when we count the mass number for our neutrons there, because there's two of them, that's a 2 up there up on top, along with 96 and 138 will give us 236 on the right, and 235 and 1 will give us 236, obviously, on the left there. Now, for the other numbers that are there, we also need to make sure that we balance out the atomic numbers. So the atomic numbers on the left-hand side need to equal the atomic numbers on the right-hand side. So again, that is how we balance a nuclear reaction. So for example, let's just say we took this one here, and let's just say that something was missing, like we had something like this. And we'll just do this guy here. We'll do 96, 37. I'll come down here. And what you would probably want to start with is obviously the atomic number, because if you can figure out the missing atomic number, all you have to do is find a periodic table, right, and find what element's missing. So on the left-hand side, we have 92. On the right-hand side here, we have 37 and basically 0. So basically at this point, to get it to 92 on the right-hand side, 92 minus 37 is going to give us our missing atomic number, which is 55. We would go to the periodic table, find number 55, and again, number 55 that's sitting there is cesium. We would do the exact same thing for the top. We would add up the top, which is 236 on the left. On the right-hand side, we have 96, and once again, we do have to multiply that 2 plus 2, which would give us 98. And again, we just subtract at this point 236 from 98, and that's where we do get our 138 from, and you can find your missing sort of guy. So sometimes you'll have equations like this where something is missing, and that's usually the best approach, is kind of start with the atomic number, figure out what element's missing, and then get the mass number from it. Now, sometimes what is missing is not an element. It could also be a particle, perhaps. So it could be something like a neutron, an alpha particle, or something like that. So if you kind of look and you can't really find an element that maybe matches or something like that, then think about maybe a particle is missing. Now, if you have some type of decay process, again, you would put that particle on the product side and again, do the same thing, figure out what is missing. So for example, if we look at this one here together, We're going to go with PO. Again, we would go to the periodic table and we would find PO there. And PO is right there. Where did it go there? 84, looks like. So we go to periodic table, 84 is PO. That is our atomic number. So this is 21284 PO. It decays by alpha emission. So again, alpha emission means that we want to put on the product side our alpha particle, which would be this here. And again, you could also, if you wanted to, use the helium symbol for the alpha particle. It is, kind of your preference, whichever one you want to use. At this point, we could really find the missing atomic number. We have 84 on the left. We obviously have 2 on the right. So if I subtract that, that gives me a missing atomic number for the right-hand side of 82. Once again, I return back to the periodic table there, and 82 is lead. And now for the top here, we have 212. On the right-hand side, we have 4. If I subtract that, I get something like 208, I believe. And there will be now our balanced nuclear equation. Again, all the mass numbers on the left equal all the mass numbers on the right. All the atomic numbers on the left equal all the atomic numbers on the right. Any questions all out there? So not too bad. When you're balancing nuclear equations, pretty much periodic table. Maybe a calculator is necessary, but it's just adding, basically subtracting, so should be okay. So as I mentioned earlier, the main difference between chemical process and nuclear process is really what's happening in those reactions. And again, in our chemical, it's all about breaking and making bonds, all about electrons, nothing in the nucleus is touched. Nuclear reactions, all about what's going on in the nucleus. That's also why, as we'll see in a couple of slides as well, there's a major difference between the energy, for example, that is released when we do, say, a nuclear reaction versus a chemical reaction. So the really exothermic chemical reaction is way less energy being released than in, say, in a nuclear reaction. Again, if you think about the nucleus, it probably involves a lot of energy transfer to convert protons to neutrons, neutrons to protons, and play with things. Inside the nucleus, it releases a lot of energy as a result of that. So let's take a little bit about the beta decay here and kind of look at what's sort of really happening in some of these situations. So for here, we have a beta decay, which is -1, which means you actually do need to increase the atomic number by 1 in this case. What's actually happening in this case is we're taking a neutron and we're converting it into a proton, and a beta particle is being released as a result of it. We're not going to worry about the neutrino, which are these guys, no mass or anything like that. So you don't have to worry about it for us in here. So what's happening here is the mass number overall is really not changing, and the atomic number goes up by 1. In reality, the mass number is changing, but overall it doesn't change. So what I mean by that, if we sort of did this step by step and see what happens is we take a neutron and we're going to lose a neutron, which means our mass number here is going to change from 13, and we'll end up with 16 in this case. Now, what happens is we are going to give off and gain a proton in this case. So we'll gain a proton. So at that point, we now go to 14 and 17. Not set. I say 7. We started with 6. That would be much better there. 7. There you go. And 14 and 7, and we'll get to our ending guy here. So again, although it doesn't overall change, we are basically converting a neutron into a proton, and that kind of puts it back into the mass number. Says mass numbers, protons and neutrons, and overall the mass number doesn't change, but it really is swapping a neutron for a proton, and that's what's happening in that situation. Now, when we look at a positron decay, kind of the same thing happening. In this case, we actually go 1 less because this is a positive one. Overall here, again, our mass number is not changing, but it really is because we're going to convert 1 proton into a neutron. So again, if you kind of looked at it in a step-by-step fashion, I'll try to use the right numbers this time. We're going to lose ourselves a proton. which means we will end up with 10 and 5 in this case. And obviously at that point, the 5 moves us to a boron. We will then gain a neutron, which will then take us to 11, 5, and boron, where we do end up over here. So again, overall, the mass number is not changing, but in reality, we are changing a proton into a neutron. And net-wise, it doesn't change the mass number because, again, the mass number is protons and neutrons that are happening. In an electron capture, we are basically making a neutron in this case. And what's happening is a proton and an electron are coming together to make a neutron. If you just add up the bottom numbers here, 1 and -1 is 0, and 1, that is a neutron that is basically being made. Again, overall in this case, the mass number is not changing, but it sort of is as well. So again, if you kind of super slow-mo it here, we're going to take a proton here and we're going to lose a proton. That's going to take us to 36 and 17, which gets us to chlorine. We are then going to make a neutron, and that's going to get us back to 37, 17, and chlorine at the end. So again, we're kind of swapping like a proton for a neutron here in terms of our mass number. Overall, there's not going to be a net change that's occurring basically in the mass number. Probably your biggest change that you're going to see is with an alpha particle, and obviously an alpha particle is going to change the mass number by 4 and also change the atomic number by 2. And we decrease the neutrons by 2 and we decrease the protons by 2 as well. So we do see a pretty big change that's occurring here. Now, the process of fission is the process where we have an unstable nucleus, and an unstable nucleus will actually go through a decay process or a fission process. And usually in a fission process, you will get a couple of new nucleuses that are made. And you also will release neutrons as a process here of fission. And as we'll also talk about later on, that's usually involving a lot of energy that's actually going off as well. As we'll talk about, a fission reaction, for example, is the reaction that's used, say, in a nuclear power plant to provide energy and stuff like that. So it does give off a lot of energy. Fission can be spontaneous, which means you do not need to do anything for it to occur. It could just naturally sort of occur. It can also occur by you doing something like shooting a particle like a neutron at something that's stable, and it becomes kind of unstable at that point and will kind of kick off the fission process as well. Typically in a fission process, you don't necessarily always get the same products. There's a lot of products that you commonly will get, but you won't always necessarily form the same products as a result of a fission reaction. All right, so why don't you give this go? Write the nuclear equation for potassium 40. When the number is written like that, -40, that is which number? That is the mass number, yeah? Because we know we could get the atomic number from the periodic table, which, by the way, that definitely is the mass number. So we'll start with our potassium. That's a 40. We'll go to periodic table there and get our atomic number, which is number 19. Here we have a positron emission. So that is, emission means that positron particle is going to be on the product side of the arrow. Positron 0 + 1 beta symbol, or 0 + 1 E, whichever symbol you want to use there. Again, at this point, we want to kind of find our missing atomic number. That's 19, that's 1. So if we just subtract those two, that looks like an 18 is our missing atomic number. We go back to the periodic table and we can find number 18 is argon. That would be our symbol. We'll do the same thing up on top. We got 40 on the left and 0 on the right. So obviously 40 minus 0 is 40. And now we would have obviously our balanced equation. Questions on that one there? All right, then why don't you try a few more here, I think, maybe, or not? Yeah. Why don't you try these guys, balance the equations and write them for each of these? All right, let's take a look, see how you're doing. We'll start here with uranium-238. Again, that's going to be our mass number, so we'll start with that. We could go to periodic table and find uranium. That is number 92. This is an alpha emission, so again, that means the alpha particle will be on the product side. And again, you could also use the helium symbol as well instead of the alpha symbol. Here we're going to subtract our atomic numbers. So we got 92 on the left and 2 on the right. That's going to give us a 90. We once again will go back to periodic table. Number 90 TH. We have 238 on the left for the mass number, 4 on the right. So that's going to give us a 234 here. We should be good. 238 on the left and right for the mass number, and 92 on both sides. Questions on that one there? Beta emission of neon 24. So once again, we'll start with our neon, which is 24. We'll go to periodic table and see neon is number 10. Again, we have an emission, which means the beta particle should be on the product side. You could also, again, use an E for the symbol instead of a beta. Here we do want to get our atomic number, and that's 10, and that's -1, which means we do need to go one more and actually go to 11 in that case. 11 and -1 is 10, and 10 on the other side. Number 11 on the periodic table is sodium, and up on top, 24 on the left, 0 on the right, leaves us 24 there on the right-hand side. Any question on those two there? Nitrogen is number 7 on the periodic table, so we'll start with that. Again, we have an emission of a positron, so that's a 0 plus 1. Also, again, could use the E symbol. Looking at our atomic number 7 on the left, 1 on the right, which means we just need 6, and 6 is carbon. Up on top, 13 on the left, 0 on the right gives us a 13 in this case, and we're balanced. Lastly, here we have beryllium, which is number 4 on the periodic table. This is an electron capture, which means the electron will be on the reactant side, like it's being gained in this case. Pretty much in this one, all we have to do is add what we got there on the left. So 4 minus 1 is 3. That 3 means it is lithium that should be there. And 7 and 0 is 7. So we'll go up on top, which would be 7. Questions on balancing nuclear equations? Not really too bad, I don't think. Again, just some adding, subtracting in a periodic table would probably do you well, I suppose. Yeah. Any questions on that? Yeah. So the next thing we're going to talk about is actually one way that we could look at stability. And stability of a nucleus is one way that we could look at it. And a major way that we could look at it is what is known as the N to Z ratio. And that's basically your number of neutrons. And Z is the atomic number abbreviation, which is your number of protons. So the ratio of neutrons to protons will allow us to make a determination in terms of stability. There is a certain stable ratio for elements and nucleuses, and this is a picture we'll see in just a second. This is sometimes referred to as the valley of stability or the belt of stability, depending on your book. And that is a neutron to proton ratio that is considered stable. And one of two things can happen if you have something that is not stable. It will either have an N to Z ratio that's considered too low, or it will have an N to Z ratio that's considered too high to this belt of stability. And if that N to Z ratio is too high, neutrons will be converted into protons through the process of a beta decay. So if you do the ratio and it's too high, that nucleus will go through a beta decay. And what it will do is it will bring the ratio heading back down to a more stable ratio. It may actually hit perfectly stable, or it may at least move it in the correct direction to becoming more stable. If your ratio is too low, we will see one of two things will happen: a positron emission or electron capture. It could also do alpha, but it's not very efficient. So for us, we're going to stick with just these two for what will happen if it is too low. And by doing so, what's going to happen is it's going to bring that ratio back up. Now, for example, why do you have an option of both of those? If we look at the one we just did, for example, right here, this was an electron capture beryllium-7. If we did instead a positron emission, and we started with our same thing, 7 for beryllium, since it's a positron emission, it would actually go on this side. And we would end up with 3, 7, and lithium. You will end up with the exact same outcome if you do either an electron capture or a positron emission. So again, if your ratio is too low from the belt to stability, you have that sort of option to do either one. And again, we're not going to kind of do the alpha decay, but technically you can, but it doesn't work as good as positron or electron capture. So too high beta, too low positron emission and stuff. How do you know what is a good ratio? This is, I was talking about before, this yellow is sort of our belt to stability, our valley of stability. And if your nucleus is atomic number 1 through 20, a stable ratio is 1, basically. If you're from 20 to 40, a stable ratio is 1.25. And if you're from 40 to 80, the N to Z ratio is 1.5. If you're above 83, which is 84 and above, it's pretty much going to be radioactive, so you don't have to worry about calculating it. It will do that. Now, we're going to use these as pretty hard cutoffs. So what I mean by that is either it's 1 or it's too high or too low, or it's 1.25 is too high or too low. There is in reality some gray areas where you may find in a book problem or something like that, sort of a grayish area. And as you can see here, this one ends at 20 and begins at 20. This one ends at 40. This way begins at 40. So sometimes the book will go, well, it's kind of in that grayish area between, and it's okay either way. So we're going to use these as hard cutoffs. I will try not to give you one that falls right in the grayish area there. So it'll either be too high or too low, depending. So why don't you give it a try here and see what happens if we have magnesium 22? What type of decay process will it undergo, and is it stable? So that's basically magnesium 22. We could go to the periodic table there and see the atomic number is 12. So we're looking for our N to Z ratio here. So our number of protons is 12 from the periodic table. Our neutrons is going to be 22 minus 12, which gives us 10. That means our N to Z ratio is going to be 10 divided by 12. And that's going to get us here, looks like 0.833333. Now, magnesium is between 1 through 20. That means a stable ratio is 1 stable ratio. And here we can see we are too low. So in this case, we're kind of down here. We need to bring it up to our belt of stability. That can be done by, again, one of two things, either a positron emission or electron capture. So if we do that, 2212 magnesium, we'll do an electron capture here. 12 and minus 1 is 11, which is sodium. Up on top is 22. Could also, as I mentioned, do the positron emission. And again, that'll get you 22, 11, and sodium. So in this case, we end up with sodium 22. And if we look at its sort of ratio, its N to Z ratio, our Z would be 11, and our N would be 22 minus 11, which is 11. And we actually hit a really stable ratio in this particular case. You may not always hit it perfectly stable, like I said before, and you don't have to continue to write the reaction till you get to something that's stable, but it should at least move you in the correct direction. Questions on that there? All right, so let's try this one. Krypton 85. All right, so let's take a look. So obviously, krypton 85 is the mass number. We get 36 there from our periodic table. Our N to Z ratio here, obviously, we have 36. Up on top, we're going to take mass number minus atomic number, and that's going to get us there. Looks like 49 divided by 36. So give us an N to Z ratio of 1.36. In this case, krypton is falling between the 20 to 40 as its number 36. Again, a stable ratio for that is 1.25. So an N to Z of 1.25 is stable in that situation. Here we are higher than the belt stability, so we need to kind of bring it down. To do that, when we are too high, it will go through a beta decay. So we'll take our 8536. It's going to go through a beta decay. That's going to get us, I'm sorry, here go 37 in this case. 37 and -1 is going to give us 36. We go to periodic table, find number 37, which is RB. Up on top, 85 and 0 is going to give us 85 in this case. Now, when we look at this guy here that we just made, its N to Z ratio is going to be 85 minus 37, which is 48, and 37 for its protons, and 48 divided by 37 makes it about a 1.30. Again, it's not perfectly stable at 1.25, but it is moving downward towards 1.25. Again, if you did this and what you got was the ratio going in the opposite direction, like 1.4 or something like that, you're definitely going in the wrong direction, right? So you're not doing the proper process. Any questions on N to Z ratio? So this is one way that we could look at the stability of a nucleus. We could also make a prediction as to what will happen if it is not a good ratio. Other ways that we can predict stability, in addition to looking at the N to Z ratio, is the number of protons and neutrons, and more specifically, are there an even number of protons and neutrons, odd number of protons and neutrons, mixture of both? As you see from the table on the bottom, which you have a similar table, I think, in your book as well, really the best sort of situation for stability is when you have even protons and even neutrons. You can see there's 157 stable nucleuses that are in that sort of arrangement. The next sort of best thing is even protons, odd neutrons. There's about 53 stable ones. Next best would be odd protons, even neutrons, about 50. So really from this, the best situation is you got something that's at least even, right? You got a good chance you might find something that's stable. Best is even on both. Worst situation is odd on both of them. There's only about 5 stable nucleuses that have that sort of arrangement. So even's a good thing, odd, not such a great thing. If the total number of nucleons, and by the way, that is a term that you see a lot in nuclear chemistry, which is nucleons. It's basically what's in the nucleus, which basically is your protons and your neutrons. It's essentially, in most cases, your mass numbers, essentially, right? Your protons and neutrons. Um, if they add up to sort of what is referred to sometimes as a magic number, it's kind of like achieving noble gas configuration with electrons, how that makes things more stable. So if you have things that are stable when you have a neutron or a proton of 2, 8, 20, 28, 50, 82, and maybe a neutron of 126, these are also considered most stable. So you can look at stability a lot of times by the N to Z ratio. A lot of times people will look at stability based on evens and odds. Question on those other ways to look at stability. So let's talk a little bit about a decay process or a decay series, actually. And in a decay series, what happens is you basically have one radioactive decay process that occurs one right after the other until basically it hits something that is stable. So it'll kind of keep continuing this process of decaying until it hits something that's stable. Um, you can do it one of two ways. You can write out basically the nuclear equations like we did earlier when we were balancing our nuclear equations. You could also, if you want, if it is beta or alpha decays, you can just kind of do a little math problem if you all you're interested in is what you get at the end. For every alpha decay, you're going to subtract 4 from the mass number and 2 from the atomic number. And for every beta decay that you have, you're going to add 1 to the atomic number. So for example, if we had just a short decay series of uranium-238, and obviously uranium here is 92, and let's just say it went through an alpha, a beta, and an alpha. We'll just do a short little 5-stepper type process here. Obviously, it usually goes on and on for a good period of time. One way that you can figure out what's going on is just to write your equations like we were doing. So you take your 238 uranium 92. The first thing that will happen is it will go through an alpha decay, which means we will have our alpha particle. And again, that means 90 on the bottom to get us to 92 on each side and 234. Again, we go to 90 and we see TH. Now, what happens in a decay series is whatever you just made will now be what you're starting with. So it will continue to go through this process. And now this guy will go through an alpha decay. And that's going to get us to 88, I believe, and 230. Again, if we go to periodic table and find number 88, it is Ra. Now this guy will go through the next process, which is a beta decay. 230, 88 Ra. We'll go through our beta decay. Remember here, that's -1, which means we do need to add 1 more to our atomic number. Then we got 230, so 89 here is going to be a C. Again, this guy will now go through the next process, which is a beta decay. Again, we got to go up 1 more to TH, which is our 90, which is TH, and that gives us 230. And lastly, this guy will go through our last process here, which is a alpha decay, and this made up one here. Again, you can use alpha or helium, whichever one you want to use. And that's going to get us to 88 and a 226, I think. And again, 88 on the periodic table there is going to be Ra in this particular case. And obviously, if the decay process continued, you would just continue to do that. Again, your kind of parent, daughter, and then obviously the king switching and so forth. So whatever you make will go through the next process. Now, let's just say you were just interested, for example, in what you get at the end of the road there at the very end of the process. So you could take your 238 and your 92, and basically, although I scratched it out here, I'll put it here. We basically have 1, 2, 3 alpha decays. That means from the mass number 1, 2, and 3, we're going to take 4 away twice and 2 away from the bottom. We also have 2 beta decays, which means we're going to add 1 to the bottom number. So for the top there, if we did that, 238 minus 4 is 234, minus 4 is 230, minus 4 is 226. On the bottom, 92 minus 2 is obviously 90, minus 2 is 88, minus 2 is 86, plus 1 is 87, plus 1 more is 88. And you could just mathematically, again, sort of get to where you're going to end up with if you're dealing with alpha or beta decays. Any questions on a decay series here? And like I said, it typically will continue on until it kind of hits something that is stable. Questions on that there? So here is uranium 238, and as you can see, it basically kind of varies up to the first one there and goes off into a couple different processes, but it all ends up at the same spot there, which is lead 206, which is a stable one. You can see it's a fairly long decay series until it hits something that is stable. So radioactivity and radioactive decay does do kinetics. The good news is it is the same kinetics that we did at the very beginning of the semester, believe it or not, however many weeks ago that was, 14, maybe 15. It also follows first order kinetics. So all radioactive decay will follow basically first order kinetics. And if you remember first order, I hope so, we have a few things that are important, right? We have K, which is our rate constant that has units of reciprocal seconds, are basically 1 over some unit of time. Now, in regular kinetics, we call K the rate constant. In nuclear chemistry, they just call it a decay constant. So when they say a decay constant, it's the same thing as in normal kinetics, the rate constant, essentially. So you remember we had an integrated rate law for first order, which is the natural log of A is equal to the natural log of A naught minus KT. This also is the same deal as what we did before. This is your final. This is your initial. This again, in this case, is your decay constant. And a reminder that T here is time, yeah? We also have a half-life equation where the half-life is equal to the natural log of 2 divided by K. Remember, the natural log of 2 is 0.693 times K. Now, a couple of things before we get there, I guess. A reminder that the proper sort of graph that we associate with first order is the natural log of A over T, right? Gives you a slope that's equal to minus the decay constant in this case. Now, a couple of things that is different in maybe nuclear chemistry when we use these equations, it's really not all that different, is when we did regular kinetics, we basically use pretty much molarity for their concentrations, right? And that's basically what we use. And really, you don't have to use molarity. So in this chapter, we could use things like grams for both of them. You could use milligrams for both of them. You could use something like the rate of radioactive decay, like counts per minute or something like that, disintegrations per minute. So the units for kind of A here really doesn't matter. You could even use percentages for both of them if you like. The deal is, though, they do need to be the same unit. So as long as they're the same units, you're good to go. It does not have to be molarity. In most cases, you probably won't see molarity a lot in nuclear chemistry use of this equation. Now, also a reminder, as you are aware of, I hope, the unit of time for both of these do need to be the same. So again, your rate constant or decay constant, whatever you want to call it, does have to have the same unit of time as your time for that to properly cancel out. So you do want to watch the unit there, right, of time, right, for those two. Now, maybe more so than we did in kinetics, you oftentimes will use both of these equations together. So very commonly, you do need to use both of these equations together. And the reason you need to do that is maybe you're solving for this guy or maybe you're solving for this guy. But one of the things you will not be given a lot of times is the actual decay constant. But what they will give you, because it's nuclear chemistry, is the half-life. And by the way, as you hopefully remember, the half-life, right, is the time it takes for half of whatever you started with to go away. So if you had 10 of something, after the first half-life, you have 5, right? After the next one, you have 2.5, and so forth. So a lot of times you'll be using this half-life equation to solve for the decay constant. So then you can basically put it into this equation and solve for really what you're looking for. So that's a very common thing here in nuclear chemistry. Now you may be wondering about all these other symbols down here. And frankly, in nuclear chemistry, they like to sometimes use different symbols because they're nuclear chemists. It makes them feel better, I suppose. So they will sometimes use N instead of A, and N is just nuclei, just basically the nucleus, basically. So you can want to use A, you can use A, it doesn't really matter. But that's a symbol and that's a nuclide basically. And also for the decay constant, your book I don't think does it, but some books and stuff will actually use lambda for the decay constant as the symbol. So sometimes you may see that as well. But I'll be honest with you, I would just roll with the regular old chapter 13 kinetics equation, right? And just do it like you normally would. and you don't have to remember any other symbols. It all comes out the same. It's all really the same idea as to what you're using. Obviously, we could use this equation to figure out things like how much of a radioactive nucleus is going to still be there. We could also think about how much time it would take for something to decay away. We could solve for how much was originally there. So just like in normal kinetics, we actually can solve for any of these things basically in this equation. Any questions on that there? Obviously, half-lives have a different amount, and half-lives could be really long and half-lives could be really short. Clearly, you can see here in this, something like uranium is a half-life of like 4.5 times 10 to 9 years. None of us make it into one of those, right? Or you could have something like TH219, which is only 1.05 times 10 to the minus 6 seconds, which we'll all make it to, hopefully, each of those half-lives. So the application of what you may be using something radioactive with, for example, if you're using something that's radioactive in medicine, you would want something a much lower half-life, right? Than if you would want something with a really, really long half-life. Otherwise, your follow-up appointment might be way down the road. So just to show you, to finish up on here, a kinetics problem and to kind of show you the idea. If we have a problem such as this, where we have 1.35 milligrams of plutonium 236, we want to know how much of it will be there after 5 years. The half-life is 2.86 years. So again, the good thing about radioactive decay is you automatically don't have to guess what kinetics you should use. It should always be our first order equations. So you should really just start with those basically right off the bat. So in this case, we have initially 1.35 milligrams. We're looking for how much will be there at the end of 5 years. So if we look at our equation, we have the years, we're looking for this guy, we have this guy. So as I mentioned before, very, very commonly here, they don't give you the decay constant, and that is why you're given basically the half-life here. So we're going to use our half-life equation to find a decay constant. And again, to do that, we're going to rearrange it, and it'll be the natural log of 2 divided by the half-life. Gives us a natural log of 2 divided by 2.86 years. And that's going to get us here a decay constant of 0.242 reciprocal years. So again, a unit of 1 over time, like we expect for a first order here. Now we have everything that we need to kind of solve. The natural log of A would equal our natural log. And again, like I said before, you could throw the milligrams in there. It doesn't have to be molarity or anything like that. Minus our guy that we just solved for, reciprocal years, times our 5 years. This again is the situation we talked about earlier. We want to make sure that the unit of time in both of those things are the same. We actually are okay in this case, but you could have something where one is like days and one's years, or one's minute, one's hours. So you want to make sure you don't mess that up. Obviously, the years here are going to cancel. If we clean up what's on the right-hand side there, we're going to take the natural log of 1.35. We're then going to subtract it from 0.242 times 5. That's going to give us the natural log of A is equal to minus 0.909895. To get rid of the natural log on the left, we got to E both sides, right? That's going to get rid of the natural log over there. And that will give us an final sort of amount of 0.403. And the units here would be the same as our initial. It would be milligrams in this case. It's basically just a regular old sort of kinetics problem. It does make sense because it's decaying, which means what we end up with should be less than what we started with. Again, if you end up with more than you started with, you probably went the wrong way. It's not decaying, right? It's actually making stuff, right? So you want to make sure, again, things sort of make sense. Any questions on that there?